using quadratic techniques to solve polynomial equations. So you see the term quadratic, and we've heard a lot about quadratics. We did a whole bunch on parabolas. So we're going to use our knowledge of quadratics to help us solve more complicated polynomial functions. So a quadratic is of this form where we have some coefficient times something squared plus b, this is another coefficient, times just that something plus c is equal to 0. Now what we're going to use is this general equation to help us substitute some values in so that we can solve more complicated polynomials. Now we can only do this if we can write it in this form. We can only use these quadratic techniques. So for example, let's look at the polynomial x to the fourth minus 17x squared plus 16. Now it looks very close to my form up here, except for I have a fourth power here and a second power here. So I'd really like to write that as something squared. So what I've done is I want this to kind of be an x, or to a first power. So what I did was I let u equal x squared. If I do that and I square both of them, if I square u, I get u squared is equal to x squared squared, which is going to give me x to the fourth, which is exactly this. So I can substitute my values in and make it look exactly like a quadratic. So instead of x to the fourth, I'm going to put u squared minus 17x squared, which I substituted in, I have for u plus 16 equals 0. Now this looks just like a quadratic equation. In fact, it is. And so I can go ahead and factor this one. And even if I couldn't factor, I know I could solve a quadratic equation by either completing the square or using the quadratic formula. But factoring this one, I have u minus 16 times u minus 1 is equal to 0. So that gives me u is equal to 16, or u is equal to 1. I'm not really solving for u though, I'm solving for x. And so I'm going to replace that u with what I know it equals, which is an x squared. So I have x squared is equal to 16, x squared is also equal to 1. And then I'm just going to go ahead and take the square root of both sides. And this one right here is both the positive and the negative. Square root here, and the square root of x squared is just x. So I have x is equal to plus and minus 4, which is the square root of 16. And x is also equal to plus and minus 1. And I expected 4 solutions because that's a quartic. And so my solution set is -4, -1, 1, and 4. So I used my knowledge of a quadratic in order to solve a 4th degree polynomial. Let's take a look at another example. So this you may have seen before, and some of your techniques would be maybe to isolate the square root and put the x, subtract an x, and maybe add a 3 and then square both sides, but we can use our quadratic techniques as well. So if I let u be my center value here, so for the coefficient times u, I would let u equal the square root of x. Well, it happens that when I square u, I also get x, and so I can rewrite this in a quadratic form. So I have u squared minus 2u minus 3 is equal to 0. And this again factors nicely. It's like it was made to do that, but if it didn't, we could use the quadratic formula or completing the square. So this factors into u minus 3 times u plus 1 is equal to 0. So I have u is equal to 3 and u is equal to -1. But that's not what I'm solving for. I'm solving for x, and so I substitute square root of x back in here, and I have square root of x is equal to -1, which I know can't happen. So this is not a solution. I have square root of x is equal to 3. Now I know that can happen, so I go ahead and square both sides. Square root of x squared is just x, and 3 squared will give me a 9. I can actually check my value if I wanted to, substituting it back in. So instead of an x, I'm going to put a 9, minus 2 times the square root of x, which is 9, minus 3. I have 9 minus 6 times 3, minus 2 times 3, which is -6, minus 3. And I have 9 minus 6 minus 3 equals 0, and that all checks out. If I were to have substituted my -1 in here, I would see up here that I can't take that square root of my -1. So let's take a look at what I think is probably the trickiest example, and that's only because it includes fractions. So here I'd really like to write this as a quadratic. I'm going to let u be my y to the 1/3. And what I really hope is my u squared is going to give me y to the 2/3. So u is equal to y to the 1/3. And then I go ahead and square both sides. And when I square this, I get u squared is equal to y to the 1/3 squared. Now remember, when you have an exponent, you can just multiply that. And 2 times 1/3 is just 2/3. So I get y to the 2/3. So instead of y to the 2/3, I can put my u squared minus u is equal to y to the 1/3. U plus 20 equals 0. I can again factor this. So I have a u minus 4 times u minus 5 equals 0. U is equal to 4 or u is equal to 5. And then I can go ahead and substitute my y to the 1/3 power back in for u. Y to the 1/3 equals 4 and y to the 1/3 equals 5. And I don't want to know what y to the 1/3 is. I want to know what y is. So I'm going to go ahead and cube both sides because that will undo my y to the 1/3 power. When I multiply through, I'll just get y to the first power. So I cube both sides, and I have y is equal to 64 and y is equal to 125. And again, I could take those back in here, substitute my values in, and I should make a true equation here. If I don't, I know I did something wrong down here. So you can always check your answer. So my two solutions are y equals 64 and y equals 125. Now the last example we're going to look at starts off as a cubic. And you need to know the sum and the difference of cubes. So you could do this by trial and error, or you could kind of look at this and look at this formula. So x to the 3rd plus a to the 3rd. That is the same as x plus a times x squared minus ax plus a squared. Depends on what a is. A is some constant. And so if you were to do this, you could just multiply through, and you would get, and simplify, multiply through, and then simplify, and you'd get back to x cubed plus a cubed. And that would be a good exercise for you to try to make sure that you know this is true. Now, when a is negative, we could actually use this same formula right here, because if a is negative, instead of a positive a, I'm going to have a negative a. And here, I'm going to have a positive number instead of a negative number. So really, this is the same as the above one. A is just negative in this one. And so we're going to use this to solve this equation right here, this cubic equation. So I have x cubed plus 64 equals 0. And that's the same as x cubed plus 4 cubed equals 0. So I'm recognizing that 64 can be broken up into something cubed. And that's going to be helpful because then I can use my equation here. I know the sum of cubes. And so I have an x plus 4, x squared, whatever this is squared, minus 4 times x, plus 4 squared, which is 16, equals 0. Well, right away, I know one of my solutions is going to be a negative 4, because if I put a negative 4 in here, that whole thing becomes 0. So that is definitely one of them, but I know I have 3 total, because I know it's a cubic. And so in order to find the others, I'm going to use this right here and see if I can factor it, which I can't. And if not, I'm going to go ahead and use the quadratic formula, or completing the square. I have the quadratic formula down here. Negative b, which is 4, plus and minus the square root of b squared, which is 16, minus 4 times a, which is 1, times c, all over 2a. A is just 1, so I have just a 2 there. Simplifying, I get a negative discriminant in here, so I know I'm going to have some imaginary numbers. And this is the same as reducing negative 16 times 3. And so I can pull out a 4i. So if I pull out a 4i and then I go ahead and use my denominator here, I have a 2 plus and minus 2i times the square root of 3. That 3 stays inside there. And then I've solved for all of my roots. I have a negative 4 and I have 2 plus and minus 2i, 2 plus and minus 2i times the square root of 3. So that gives me 2 values there. 2 plus 2i times rad 3, 2 minus 2i times rad 3. So using our knowledge, we can actually break things down and make them easier without even having to find all of the roots through the rational root theorem. If it looks nice and we can write it as a quadratic, we can solve it that way.